Welcome back to Microwave Engineering. Today I want to talk to you about lossless transmission lines. So remember from the previous lectures, we kind of derived the general lossy case where we had resistance and conductance between the conductors in our transmission line. So we derived this notion of a characteristic impedance, which was complex, and then we also had this notion of a propagation constant, which was also complex. Okay, and remember these two parameters were very integral to the voltage and the current going down a transmission line. In particular, this thing here determined the attenuation of a wave as it propagates down a line, and it also influenced the phase factor. So if you were to take this notion here, we had this idea where the solution to the voltage looked like the following. So V naught plus e to the minus gamma z. So this represented a wave propagating to the right in phasor domain. So you have some amplitude on the wave, and I had this propagation constant here, in which if you take the square root of this thing, so you would get some big complicated expression, but at the end of the day, it'll have a real component, alpha, and then there'll be an imaginary component to it as well. So this term here is obviously called the attenuation constant, and this is the, I guess you call it the phase constant. So more generally, you have a propagation constant, which can encompass both attenuation and phase, but then when you break it down into its real and imaginary bits, you get this little real value here, which turns into a real attenuation. And then over here, you get this J term, which represents kind of like a sinusoidal phase constant here. Now, the general case of solving this, if you want to actually do the algebra, it's really nasty. And in practice, what I usually do is just leave it like this and give it the parameters and then have MATLAB take the square root of it. So there's really not much point in actually deriving the closed form expressions for these in the general case. However, for the lossless case, a lot of things really do simplify. So whenever you hear the word lossless, the general implication is obviously that R prime and G prime are equal to 0. And a lot of fun things simplify in this scenario. And most of the time you can treat your transmission lines as if they're approximately lossless. Even though no transmission line will be perfectly lossless, some of them are just good enough that by the time a signal goes down and back, that the attenuation is really not that significant. Or if nothing else, you can kind of calibrate against it anyway. So it really just helps to treat things as generally being lossless, and so that all of this arithmetic just simplifies. So what will happen is, of course, my characteristic impedance will take on its familiar value, L prime over C prime. And so that will represent, of course, the ratio of my voltage to my current, like so. All right, and this propagation constant will now have an effect on this guy up here. So when I do lossless, what you'll also find is the R and the G go away, the J's kind of multiply together, and what you get is the square root of yada yada. So let's go ahead and just do that. So you'll notice I get gamma squared is equal to J omega L prime times J omega C prime, like so. So you just kind of multiply together. I get negative omega squared L prime C prime. So now I'm going to take the square root of that, and I get gamma is equal to J square root of negative 1 omega times the square root of L prime C prime. So in this case, since that alpha is gone, I essentially just have gamma is equal to J beta. So the implication then is that for my propagation constant, or my phase constant under the lossless case, I just get omega times the square root of L prime C prime. So this is a very important little expression to keep in the back of your head. Incidentally, you can also show that there exists some corresponding phase velocity to this system here. We're not going to do the derivation here. You've probably seen it before, but the phase propagation, the phase velocity of this wave in the time domain is going to be omega over beta, like so. So just remember that equation as well, which you'll notice evaluates to 1 over the square root of L prime C prime. So we're going to just not worry about that derivation. You've hopefully seen it before, and if not, it's a pretty straightforward derivation that can come out from just looking at the time domain here. So what else can we do? No, that's basically all we care about. So these are some special simplifications that happen whenever we're talking about lossless transmission lines. So my J beta turns into a very simple expression. I get a nice simple expression for my phase velocity. And of course, my wavelength will be 2 pi over beta as well. So a lot of this stuff gets more complicated in the general case, but by and large, things are pretty straightforward enough that you can just keep all these expressions in mind. Okay, so that's just some of the basic simplifications that happen when you make the lossless assumption for a transmission line. And there's a lot of great practical value in treating transmission lines as though they're lossless, even though technically they're not. Usually their lossiness is so small that it doesn't really impact the accuracy of these expressions. Okay, so we'll talk more about that in the next lecture, but just kind of make a note that these are very important little relationships that are going to come up time and time again. So just burn them into your memory.